Let us now look at the agenda for this webinar. We will first look at why we should model dispersion from a vent release. Then we will look at how fast does dispersion modeling and how we can then use the program to get dispersion results from a vent release. Last but not least, we will then look at the situations in which we will use a CFD tool like KFX to model the vent release. So here is a slide on the background of vent dispersion modeling. So venting is a widely used method for disposal of unwanted gases which are produced in the process industries. So in order to ensure that the hazard from the venting is safe to the people located nearby, we then have to look at whether my vent stack height is appropriate or not. How far will my flammable cloud travel to? Will it be able to reach an area of ignition, which then leads to an ignition of the cloud, and this will then give off radiation or explosion effects. If there are toxic components in my gas mixture, then I need to consider will the concentration of the toxic component, for example, hydrogen sulfide, will it be tolerable at the ground level where most of our population is located. And lastly, we might want to consider what is the shape and the size of the cloud. Now let's look at how we can model dispersion and hazard analysis using FAST. So first, we will define the process conditions and the release scenario. Then FAST will split the consequence analysis into three main stages. The first stage is the discharge stage, whereby we are going to look at what will be the conditions of your material as it exits the vent or a certain exit point from a pressure or a pipe. Then the next stage is the dispersion stage, where we will look at the shape and the behavior of the cloud as it spreads downwind. We look at for vapor cloud, how far the cloud will travel to, how does it mix with air, and what will be the concentration levels reached at different locations. If there is liquid in my release, then I'll consider the droplet formation, pool formation, and pool vaporization, and the resulting dispersion from the vapor coming from the pool. So all of this is taken into account in the dispersion calculations. We also take into account the effects of weather. Is it sunny weather, nighttime weather, daytime weather into our dispersion and effects calculations. The last stage is the effect stage, where we look at the toxic effects from a toxic cloud. If it's a flammable cloud, then it can get ignited to give radiation and explosion effects. So we are going to focus now on the fast dispersion model. We call it the Unified Dispersion Model, in short, the UDM model. So there's extensive continuous verification and validation, okay, for the past 35 years with the latest experimental data that is available. So if you look at the technical documentation section in the program, you'll be able to find a UDM validation document. This gives us all the information of the validation results with a real-life experimental data. We have also published many different papers over the years, okay, which you can find them on the internet. If you'd like to have a copy of these papers, to let us know, we can send them to you. So the UDM can model various different kinds of clouds, for example, a continuous cloud or instantaneous cloud or short duration cloud. We also take into account various effects in the dispersion calculations, whether your cloud is buoyant or not. If there is liquid in the release, I can have droplet formation, rainout, pool formation, pool vaporization, cloud touching down, cloud lifting off, or it can caps up the mixing layer. We also consider how the cloud mix with air in the atmosphere, air entrainment, and cloud spreading. The UDM also predicts the full range of expected dispersion stages. For example, we have the initial turbulent expanding jet phase, then the heavy gas spreading phase, or buoyant elevator phase, and lastly, we have the passive dispersion stage. If you'd like to learn more about the theory of dispersion modeling, we do cover them in more detail in our training courses. Next, let us look at how we can model the dispersion of a release from a vent using FAST. So first, we will have to set up the equipment and the release scenario. So we set up a pressure vessel equipment item in the program, and we are going to define the operating pressure and temperature, the material or mixture that will be released, and lastly, how much of this material or mixture released. So we look at the inventory. Then we set up a short pipe scenario. Underneath the equipment item, we will specify the pipe internal diameter, which will be the same as the vent diameter, the pipe length. If you know the flow rate, so if you know that fixed flow rate coming out from the vent, then you can set up a flow controller control valve option and define your fixed flow rate. We have a case study here whereby we are going to look at a release of a vent gas with the composition as follows: 80% bimolar methane, 5% bimolar ethane, 0.1% hydrogen sulfide, 10.9% carbon dioxide, and 4% nitrogen. We have the operating conditions as follows: 3-bar pressure, 3-bar gauge pressure, 15 degrees Celsius temperature, 1 million kilograms inventory, vent diameter 200 millimeters, pipe length and elevation to be 60 meters, and the vent volume rate 2.1 million cubic feet per day. That will be converted to a vent mass rate of 12.1 kilograms per second. So we are going to look at how we can model that in FAST. So I'll cover this in more detail during the demonstration later on. So this slide here is for your reference. So we set up an equipment item, the pressure vessel, and the short pipe scenario, and we specify the input data that we have mentioned earlier in the previous slide into the equipment item and the scenario. Then what are the results we can get for dispersion? So over here, we can see the graphs. We have a dispersion main tab on the graph, and you can see all the dispersion graphs that are available. So we have graphs for concentration versus distance, footprint, maximum footprint. And here on this slide, we are highlighting the side view graph. Now for the side view graph, you can see for your concentrations that you are interested in. In this case, this is the flammable concentrations, UFL, LFL, 0.5 LFL concentration. You could see how high your cloud concentration will reach and how far the distance downwind that these flammable concentrations reach. I can also add a background image to my side view graph. So here I've inserted a side view image of a facility, and I can see the size of my flammable cloud in respective to other equipments and units in the surrounding area of the vent. So you want to see, for example, whether this flammable cloud has any potential to reach an area of ignition. Because then you don't want ignition to happen, then you get radiation and explosion effects. If there is a toxic component in my mixture, for example, in this case, hydrogen sulfide, I could choose to track the concentration of a particular component. In this case, I can choose hydrogen sulfide here as the material to track. I can also define my concentration of interest. So let's say in this case, I'm interested in 2 ppm hydrogen sulfide. Then I set the averaging time to be toxic. And over here on the side view, you can see that my material to track is hydrogen sulfide. And this is showing me the cloud for 2 ppm and 10 ppm of the hydrogen sulfide material in the mixture. Next, we are going to look at the demonstration in FAST. So over here, okay, I have set up some cases which I'll talk about later on. But the first thing we always try to do is, if you have a mixture especially, is to set up the mixture in the program. So in this case, I'm going to go to the Materials tab over here. And here I have set up a mixture called the vent gas. Now to set up a mixture, what I need to do is to right click on the Materials folder, choose Insert, and I choose to set up a mixture. So here I have the mixture set up already. I'm going to double click on this mixture. So what I do is to choose the components and move it to the right to select the component for the mixture. I can also define the mass amount or the molar amount. Now, more of this detail in how we look at materials properties, how we set up mixtures, mixture properties. These are all covered in more detail. Later on in August, we have a webinar that is focused on the topic materials and mixtures. Okay, so I've set this mixture up, and I'm going to go to back to the models tab over here. So to set up a vent release, we have to first set up an equipment item. So to do that, I'll right click on this vent dispersion example folder, insert, and here you could see all the equipment items that can be specified. For this case, use the pressure vessel. We are going to use the pressure vessel. And then I have a pressure vessel that is inserted here already. I'm going to double click on this pressure vessel. And these are the input data that we need to specify the material or mixture to be released. In this case, we set up the vent gas mixture. We use that as the gas to be released. The mass inventory, 1 million kilograms. Again, you can choose to specify volume inventory as well. 15 degrees Celsius temperature, 3 bar gauge pressure. So that's the operating conditions for my equipment item. Then next, I want to set up the short pipe scenario. So I'm going to right click on the equipment item, insert. This is where you can set up the scenario. So in this case, we are going to use the short pipe scenario. So I have one set up here already. I'm going to double click on this vent release. And for this short pipe case, I'm going to set my scenario type to be line rupture, pipe internal diameter 200 millimeters, pipe length 60 meters, elevation 60 meters. At the flow controller option over here, because I know the flow rate, so I set it to be control valve. I set the fixed flow rate to be 12.1 kilograms per second, like what we saw in the slides earlier. I'm going to set my outdoor release direction to be a vertical release. So after I set up the release, I just have to run the scenario. Okay, and once it has finished running, there is a green tick here next to the release. I'll be able to view the results. So here we are going to look at the graphic results for this release. So I have one open over here. So we can see a main dispersion tab with all the dispersion graphs that are available, like concentration versus distance, footprint, maximum footprint, and so on. Here we are going to focus on the side view graph. The red contour here represents UFL, upper flammable limit. The green contour here represents lower flammable limit, LFL. And the blue contour here is 0.5 times lower flammable limit. So I can see here how high my cloud will travel to and how far the distance downwind my cloud concentrations will reach. Then over here, I can also choose to insert a background image. So under the configuration tab, I can choose to set up a background image over here. And I could see the size of my cloud in respective to the units and equipments they are located around the vent. Lastly, we're also going to look at what happens if I want to track a particular component in the mixture. So I shall double click on this second pressure vessel over here. Under the material to track, I'll be able to choose to track the concentrations of any material in the mixture. In this case, I'm going to choose hydrogen sulfide, which is a toxic component. And under the dispersion tab, okay, I could choose to track the concentration of interest. In this case, I set it to be 2 ppm hydrogen sulfide. So then I run the case, and I'll be able to see, in this case, this is my side view graph, okay, of my of the same, at the background image of the same facility. You'll be able to see the side view graph of tracking the 2 ppm, 4 ppm, 10 ppm H2S in this graph over here. So you can see whether it's your H2S cloud concentration, did it reach the height at which populations are located. So in this case, it's quite high up, so it's not affecting people at the ground level. So that's for the demonstration in FAST. We are now going to look at how we model event dispersion using KFX. So KFX is the CFD simulation tool that we have. Okay, so in what situations do you consider using a CFD simulation in KFX? So you might want to consider using KFX when your dispersion cloud may interact with very complex geometry, and you want to take that into account to check if my vent gas can reach an air intake location, or whether my vent gas can actually reach a location of an ignition source, because we don't want the cloud to be able to ignite. We can also want to consider if my dense gas cloud will be able to interact and reach an area of complex terrain. If I want to model an upwind release or a crosswind release, okay, you can use KFX for that. In FAST, we only model the downwind release. And lastly, you might want to consider if I have multiple vent sources that are operating simultaneously, then you want to look at the combination of the cloud dispersion. So you can also use KFX for that. So in this case here, I have a offshore facility. Here I will have multiple vents. So I want to consider the effects of having two of these vents that are operating at the same time. Okay, so I have a north view of the platform, top view of the platform, and the east view of the platform. We are going to look at, in this case, the north view. You can see how the clouds for two vents that are occurring at the same time. Okay, the cloud that's released from these two vents and how they combine for the far field. This is the top view. From the top view, you'll be able to see that the wind direction, okay, is sort of diagonal on the from the platform. So you can specify your wind direction and model it, whether it's upwind release or crosswind release or downwind release. And lastly, we have the east view. Okay, so these are what the results you can get for dispersion using KFX. So on the next slide, okay, these are the other results we can get for dispersion. You'll be able to see the concentration of your, the side view concentration of your fuel gas. This is the side view and this is the top view. So you'll be able to see if the flammable concentrations did reach an area of an ignition source. So in this case, it didn't. Okay, so we are sort of safe for that. And you can also see the effects of a particular toxic component, H2S. That's the side view of the H2S dispersion on the platform.
You may find our Ask the Expert webinar plan on the screen. Our next webinar will be held on 16th of June, and the topic will be flare radiation modeling. You will be welcome to attend again. Thank you again for attending this webinar. We hope you enjoy the session and see you in June. Bye.